There are so many ways to solve multiplication problems, and this is one way to have a configuration like so. We have 5 columns and 3 rows, and that will help us solve 5 times 3 or 3 times 5. If we count the total number of pom-poms, we find the answer to this multiplication problem. We find the product. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the answer would be 15. Suppose that I want to show that 5 times 3 is equal to 3 times 5. We can also use this configuration and group it in a certain way to show this. So I grouped the pom-poms like so. Let's find how many pom-poms are in each group. 1, 2, 3 pom-poms here. 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 We want to find what the total number of pom-poms is, so we add them all together. We add all the 3's together. And 3 plus 3 plus 3 plus 3 plus 3, we're using repeating addition, the definition of multiplication. We have 5 3's being added together. So that is equal to 5 times 3. So the number of pom-poms we have is 5 times 3, which is 15. I grouped the pom-poms in another way, grouping by rows instead of columns. Let's see how many pom-poms we have in each group. 1, 2, 3, 4, 5. 5 pom-poms in this group. 1, 2, 3, 4, 5. 5 pom-poms in this group. 1, 2, 3, 4, 5. And 5 pom-poms in this group. We want to know what the total number of pom-poms is, so we add these numbers together. So we have 5 plus 5 plus 5. We have 3 5's, and we're adding them together. So this is equal to 3 times 5. So one way of grouping the pom-poms, we found 5 times 3. That was using the grouping by columns, which was identified by the green yarn. For this way of grouping, we found it to be equivalent to 3 times 5. The number of pom-poms did not change, but the grouping did. And so we can tell that 5 times 3 is equal to 3 times 5. So we know that A times B equals B times A works when you're dealing with only positive integers, when you're dealing only with counting numbers. Now, let's see about the cases in which we have other numbers. For this example, I decided to use crackers to vary it up a little bit and also make it easier to cut each piece in half. This configuration can be used to show that 2.5, that is 2.5, times 4 is equal to 4 times 2.5. This is our example for a positive number that is not an integer times a positive integer. So I grouped them up like so, by columns. Let's see how many crackers we have in each column. 1, 2, 3, 4. 4 crackers in this group. 1, 2, 3, 4. 4 crackers in this group. 1 half, 2 halves. 3 halves, 4 halves. So a half of 4 in this group. We want to see what the total number of crackers is, so we add up these numbers together. We have 4 plus a half of 4. We have 2 and a half of 4. So this is equal to 2 and a half times 4, or 2.5 times 4.
I would like to quickly explain why 1/2 of 4 is equal to 4 1/2. As you can see in this picture, I took a half of 4 crackers, and that ended up being 1/2, 2 halves, 3 halves, 4 halves. So, a half of 4 is equal to 4 1/2. Another way to think of a half of 4 is like so. I would like to show why in this picture as well, 1/2 of 4 is equal to 4 1/2. We have in this picture 1 half, 2 halves, 3 halves, 4 halves. So 1/2 of 4 is equal to 4 1/2.
So I grouped them according to rows this time. Let's see how many crackers we have in each group. 1, 2, 2 and a half in this group. 1, 2, 2 and a half in this group. 1, 2, 2 and a half in this group. 1, 2, 2 and a half in this group. We want to find the total number of crackers we have. So we add these numbers all together. We have 4 2 and a halves. So this is equivalent to 4 times 2 and a half. In the previous grouping, when we grouped according to columns with green yarn, we found that the total number of crackers was equivalent to 2.5 times 4. In this grouping, we found that the number of crackers is equivalent to 4 times 2.5. The number of crackers did not change between the groupings. Only the groupings did. So therefore 2.5 times 4 is equal to 4 times 2.5. So now we know that this property, that A times B equals B times A, works when you have a positive number that is not an integer and a positive integer. But what about if you have two positive numbers that are not integers? In this example, we'll be using rectangles of chocolate. In this example, I want to show that 2 2/3 times 3.5 equals 3.5 times 2 2/3. So I grouped them according to column. Let's see how much we have in each group. 1, 2, 3, 3 and a half. 1, 2, 3, 3 and a half. 2/3, 2 2/3, 3 2/3, 3 and a half 2/3. Now we want to add them all together to figure out what the total number is. So we have 1 3.5, 2 3.5s, 2 2/3 3.5s. And so that is equal to 2 2/3 times 3.5. So I grouped them according to rows this time. Let's see how many we have in each group. 1, 2, 2 2/3. 1, 2, 2 and 2/3. 1, 2, 2 and 2/3. 1/2, 2 halves, 2 and 2/3 halves. We want to figure out what the total number is, so we'll add all these together. We have 1, 2 and 2/3, 2, 2 and 2/3, 3, 2 and 2/3, 3.5, 2 and 2/3. So this is equal to 3.5 times 2 and 2/3, or 3.5 times 2 and 2/3. As you can tell, in the last grouping, when we grouped according to columns with the green yarn, we found the total number to be 2 and 2/3 times 3.5. In this grouping, we found the answer to be 3.5 times 2 and 2/3. Since the total amount did not change, but only the grouping did, 2 and 2/3 times 3.5 must equal 3.5 times 2 and 2/3. So as you can see, this property that A times B equals B times A works when you multiply two positive numbers that are not integers. Since we've gone over all the types of cases for positive numbers, this property works for all positive numbers. But what about if you multiply a positive and a negative number together? But what about if you multiply two negative numbers together?
Part 3 is about those cases in which you include negative numbers. Attached is a link that you can click if you would wish.